Hello everyone, my name is Anudeep. Today I am presenting the paper titled Deep Residual Learning for Image Recognition. This uh, this is the main page, and let's go to the next slide. The title, the title page. So this influential paper was written by Keming He, Zhang, and Shouqing Ren and Jian in 2015 year. It was published at the prestigious CVPR conference, which focuses on computer vision and pattern recognition particularly. This paper introduced a new method called residual networks, or ResNet, we can call it, which changed how deep learning models are built and trained actually. It specifically solved the problems in training very deep neural networks. So let's go to the next slide, which is the data. So the authors trained and tested their models mainly on the ImageNet dataset which they have used, which is one of the largest and the most popular datasets in the computer vision sector. And ImageNet contains over 1 million images spread across 1,000 different categories like animals, vehicles, and everyday objects, etc. Because of its size and the variety, ImageNet is a standard benchmark to test image classification models. The paper also tested the model on other tasks like the object detection using the MS COCO dataset to show how versatile the model is. And let's go to the next slide, which is the models. So the key innovation in this paper is a residual network, or we can call it as ResNet in short form. Normally, when we train deep neural networks, each layer tries to learn in direct mapping from input to output. But particularly in this ResNet, which is the residual network, instead of learning this direct mapping, the network learns the difference or the residual between the input and the output. This is done using the residual blocks that have skipped the connections, parts that skip one or more and directly add the input to the output of a block. This architecture helps solve the problem of vanishing the gradients, which makes the training very deep networks hard. Thanks to this, actually, ResNet models can be very deep, up to 152 layers in the paper, and still train effectively. So let's go to the next slide. So this is a picture for the residual learning, and let's go to the next slide, which is the results. So the results in the paper show that the ResNet significantly outperforms the previous networks on the ImageNet classification. Specifically, a 152 layer ResNet achieved a top 5 error rate of 3.57 percentage, which was really way more better than all the previous methods at that time. Importantly, the paper shows a graph comparing the error rates of the networks with the different depths, unlike earlier models where the performance degraded as the networks got very deeper. ResNet performance improved the consistency with depth. This was a big breakthrough because it proved we could build deeper networks that actually work better. So coming to the next slide. So this is a picture I was talking about for comparing the error rates of the networks with the different depths. And coming to the next slide, the findings. So the paper's main findings are that the residual connections make it easier to train very deep networks and allow these networks to generalize better to new data. The idea of learning residuals instead of tight mappings simplifies the optimization. The skip connections let the gradients flow more easily back through the network during the training, preventing the problems that normally occur in the deep networks. This simple idea turned out to be very powerful and influenced many later models in the computer vision and beyond. ResNet showed that the deeper networks could be stable and very accurate, which was a big step forward. And coming to the next slide, what did I learn? So from this paper, I learned the importance of the model architecture in the deep learning. The idea of residual learning is very clever because it helps with the practice problem of the training deep networks. I also understand why the skip connections are really essential. They help the gradients flow and make the deep networks easier to optimize. This paper highlights that sometimes small changes in the design can have a very big impact on performance. I also learned that the deeper the networks are not always better unless designed carefully. The concepts here are useful not just for the image recognition but for any task where the deep networks are used. So coming to the next slide, the criticism of the paper. So the paper has many strong points. It introduced a groundbreaking idea that has become a standard in deep learning, and experiments are very design and thorough. So the model size also grows with depth, making it harder to use in the real-time applications. Despite these, the benefits clearly outweigh the drawbacks. And coming to the next slide, can you apply it to your project? Yes, definitely I plan to apply the ResNet architecture to my project, which involves the image-based recognition, emotion recognition. Using pre-trained ResNet models, I can extract powerful features from images. And coming to the final slide, the conclusion. To summarize, this paper introduced the residual networks, a simple but powerful solution for training very deep neural networks. ResNet models achieved state-of-art results on the large-scale datasets like ImageNet. So understanding its ideas is valuable for anyone working on the deep learning projects, including my own. Thank you.